All right. Good morning, everyone. Let me see. I guess some people took the optional seriously. It's about half. Yeah, storm. People might have gotten caught up. All right. So the goal of this is to actually get you using Skyline a little bit. But I'll start with a little bit of introduction because I haven't even introduced Skyline to you. How many of you have heard of Skyline? Okay. How many of you actually use Skyline? Okay, just a few. So yeah, a lot of what you're going to learn here, you could do all in Skyline, and certainly you could supplement anything you're doing with Skyline. And so today, you've built a library, right? You've done a peptide search in Comet, and then you built a library out of that with Spectrast, and then you built a set of peptide query parameters for DIA out of that, right? That's what you did yesterday. How many people completed that yesterday? Okay. So luckily, there's also a completed folder on the VM. So even if you didn't complete it, we can work with completed data because it's all on the VM. So Skyline has grown from targeted proteomics environment to a targeted mass spec environment. I don't seem to have any power. I'll just go like this. Okay, so yeah, now it supports both proteomics, peptides, and small molecules. At its heart, when I was trying to describe what Skyline is, because it was once it was a SRM tool, but it now does sort of anything where there's chromatogram extraction. And today, this morning in the SkyJam, we're going to focus on one particular application, MS1 chromatogram extraction. And but it could, obviously it can do data independent acquisition, and it can do PRM as well. And I'm going to go over that in more detail when I introduce Skyline. But we're going to work exclusively with the DIA data. The way you've just worked, you haven't done any DIA yet, right? All you've done is taken DIA data and turned it into a library and then a set of query parameters. So Skyline can do a lot more with DDA data, but we're just going to use it to inspect the quality of our libraries. Okay, so we've got this data that's intended to be used for a library with DIA. How many of you know how good it is? You just built the library. What's your assessment? Is it a good library? Is it a bad library? Does any issues with it? So you don't know yet, right? But with Skyline, you can get some sense of what the data is that you're putting into your library is like. And so Skyline is capable of starting with DDA acquisition. This is how many of you have done DDA acquisition? So okay, pretty much everybody. And you do peptide searches. How many of you do peptide searches with Comet? Oh wow, look at you, mascot. Okay, good. So and there's a bazillion of them, and this is still not working. But so once you've done this is DDA. This is a schematic showing DDA acquisition. Most of you've done it and you understand it. So it's just picking in general the most intense ions it sees in MS1, and then fragmenting them in MSMS. And then you're familiar with spectrum matching, which you can do in any of these ways, and Skyline supports all of them. So how many of you do spectrum matching with some tool you don't see up here, or some pipeline you don't see up here? If you do, go ahead and contact us, and we're always happy to add more. We've been at it for almost a decade, and it's become Skyline's library building has become sort of a hub for other tools are using the libraries that we produce and stuff, and it's because pretty much any peptide spectrum matching that the field does, we support. So, and then this is what we're going to do today. the blue part. We're going to build our own spectral library, and then we're going to do chromatogram extraction with Skyline from MS1. So the chromatograms are coming from the MS1 scan. So we do the spectrum matching. We're going to build a library out of that, and then we're going to look for our peptides by extracting them out of the MS1 scans. Because in DDA data, that's the only data that's collected systematically over time, right? The MS are kind of jumping around all over the place, so you can't actually get a chromatogram that you would use for quantification. So all we can do is extract out of the MS1 scan. So that's what we're going to do. Lots of tools do this. Probably the most well-known are MaxQuant and Mascot Distiller. Basically use these IDs, and then they extract MS1 chromatograms. And if there's an MS spectrum that's identified as a certain peptide that happens in the middle of that extracted peak, then we have a lot of confidence that that peak and the area under that peak represents our peptide. This is what that looks like in Skyline. So this is a multi-replicate data set. If you're not familiar with Skyline, these are the targets, the things that Skyline is looking for. These are retention times, and these are peak areas. And then that's the chromatogram that was extracted out of MS1 and Skyline. And then these are spectra that were matched to this target peptide MFLSFPTTK, right? And then we see where the IDs were that are used to give us more confidence that that's the right peak. Why don't we get an ID right in the middle? Wouldn't we prefer to be getting an ID right? We get an MS spectrum right in the middle of the peak. Why are we getting them here and here? It's the points that the MS2 was taken, but why can't we just have a mass spectrometer take the MS2 right in the middle? What? Yeah, so there's two things, right? As soon as it gets high enough, it becomes the highest peak that the mass spectrometer can see. So it goes, boom, and I'm going to take an MS spectrum. And actually, with sort of the paradox of faster mass spectrometers is that they will take that first spectrum closer to the baseline, because they're always looking for something. And then there's some dynamic exclusion. And that looks like maybe 20-minute dynamic or 20-second dynamic exclusion or something. Like then all of a sudden it's on the list again. And we take it. And some people, to combat the fact that the MS gets taken so low, will set their settings so that something doesn't go onto the dynamic exclusion until it's been seen twice. So all this you can visualize in Skyline. Who can tell me what type of experiment this is? The peak area plot gives you a good indication. So this is the intensity of each one of the measurements over the samples. So it's a response curve or a calibration curve experiment. So this is like very, very telltale. It's sort of stair-stepping down, and then it's 3 cycles, so measured in triplicate. So Skyline will do this for any one of these 5 instrument vendors, and soon to add Shimadzu. Okay, so the thing we're going to be looking at is one of the things we're going to be looking at today when we look at our spectral quality, our data quality of the runs that we're using for our spectral library that you just built your spectral library out of, is we're going to look at how good the IRTs are. So did we get enough of a basic understanding of IRT that you understood yesterday when you created your query parameters? Those query parameters contained a spectrum or just relative intensities of all the fragment ions, as well as a retention time or a normalized retention time called IRT that would help the software find your peptide again. So that's the 2 pieces of information that get put into those query parameters. So this is This is from a data set that it was, the original Navarro data set, except that we were using a special library that we got from Diagnostics in validating DIA umpire. And this is what, when I went and looked at the retention time regression, and so this is a residuals plot. So this is how far each peptide was found from where it was predicted to be, right? And so what do you notice? Okay, so these are the I guess these are the IRT scores. Ben explained that we don't start at 0. We start at IRT somehow goes from like -20 to 120 or so. And so these are the IRT scores, and that led us to predict some time that we would see these peptides. And then in the DIA data, this is extracted from DIA data, these are the actual times that we saw these things. And I looked at this and said, oh, I think there's a problem. And why did I say that? Yeah, there's a difference in density, which just sort of tells us that maybe there, we extracted more peptides here, in this range. So there's some density of things that we're querying, and they're more dense here. What are the extremes of the points? The gradient is not that stable, or well, why do you say that? So it's 10 minutes, right? And so I actually, this is my extraction window. So 10 minutes is how wide a window I allowed Skyline to look for my peptides in. So the fact that where I was finding things are actually crushed up against the edges, you see sort of cutoffs. I would also say that I see some evidence of a curvature in here. Like why is it kind of going, So I looked at this and went, okay, I'm going to just throw open the retention time window and see what I see. And so when I went to plus or minus 15, this is what I see. And so that tells me that my IRTs are not so great, right? Like measured on some different chromatography. And you needed at least a 20-minute window to really capture most of them. And we'll talk about that more. So we're going to look at stuff like this to assess what's the data quality of the IRTs that you just built. And then we're going to decide that this morning. Okay, and so then this was some different data, Bruker data that I got. And this was Skyline's original library builder. Just sort of the sort of simplest, what I thought was not a fairly reasonable way of building spectral libraries from DDA data, produced something that when I went and then extracted everything from my DIA data, then I got correlations like this. This is my own library that I built from some DDA data that the Bruker gave me. And so what do people see here? Actually, I got little lines as hints. What do you see here, and what's the problem? What? No, it's not temperature in the lab. I mean, this was actually, we improved the library builder based on this, but certainly, well, what do you, like, so I've just shown you two sort of problematic, what do you want to see here? Yeah, I mean, boy, would we love to just see a line going right across on 0, right? That would be the ideal. I found everything exactly where I predicted it to be. And certainly having it centered on 0 and more like, no wider than half a minute would be awesome, right? So here, I'm going it's better. It's actually better than before. There's nothing extending out to 15 minutes. This is everything fits within a 5-minute window, but when I do that scoring that Ben was talking about, the retention time just isn't a very powerful score because of this effect, right? It's not aligned on my predictions. And then I was like, well, what the heck are these things? Like, it looks like a rocket ship, right? About to take off. So it turned out that this was, I don't know how many runs, I think maybe 6 runs, and we were aligning every run based on the IRT peptides in the run, and then we would and so these are just, so the IRT peptides themselves turned out not to be the most stable way to align these things, and these are peptides that are only found in one run. And so it's just showing you that like when I could average the peptides, they would end up in this mass, and when there were just peptides that came from a single run, then they ended up, like having some different alignment. And that led to, when we did the scoring, this is DDA scoring, this is sort of the M-profit distribution, and we get a set of scores. The weights for retention time, you sort of have to take this difference and squared difference, and so it's like about a 4%, when the really good scores are like 30%, right? So not retention time, not so great there. And then what I did was I imported into Skyline, exactly what you're going to do, import the data into Skyline, and then I just recalibrated the IRTs based on where the peaks were instead of where the spectra were identified. That's what, you just built a library where you built the IRTs out of where the spectra were, right? Your libraries are not looking at the MS1 at all. And then I got this. And so this is, this is a lot closer to the ideal. There's really, most stuff is lining in up within a half a minute. There's one other weird effect here. Can anybody identify what it is? Yeah, what are there's some sort of, it's not just random outliers, right? There's these 2 lines. There's, for some reason, outliers like to go pretty far away. And again, this is my 5-minute mark. I have only given myself 10 minutes to do this. So the fact that they're going out to the end is something weird, which I can now explain. But at the time, I was like, what is going on there? But once you do that, retention time becomes a really powerful score. Again, you have to sort of subtract these 2 and go, wow, it's up to about 30%, which is about the same as the library and the coelution count. The reason we get things lining up, and I'm thinking about actually removing this score, retention time difference squared, when retention time difference squared flips to negative like this, then sometimes peptides sort of break out of the scoring system, and when they're really far away, all of a sudden they have a super high score. So it's like, wow, that's great. So that's why you get this weird thing on the end. So the retention time squared is a weird score, and it may go away in Skyline soon. And then when I actually looked at the data, again, you're going to get the chance to look at your data like this. In Skyline, here are the IDs. Here's an ID over here, and then you can see that there's peak tailing, and all these light blue lines are where the IDs are in all the other runs. So you can see that it's, it goes pretty far out here from the apex of the peak. And then occasionally you get these weird things like, so they in this run, they'd put too much of the IRTs in, and that caused problems. But yeah, because of the tailing, so it turned out that what I was doing originally was taking the mean values of where I was seeing these IDs. And so, the mean of this one might be here, or maybe it's out here. But like, if I only had 2 values and they were here and here, then my mean would be there. And so I ended up switching to using medians. And in some cases where I knew that I had a tailing peak or a tailing peptide, 2 of the diagnosis IRTs are prone to tailing. And for those, I'm using 30th percentile instead of median. So this is actually last year's library. So Ben recollected all the data, and I guess a spoiler alert, it's actually, the IRTs are actually pretty nice. But these are the IRTs that we got. This is from the Spectrast library last year, and when you looked at where you found the IDs versus, where they were predicted, you got this. And that was because it was collected fractionated, and there were a lot of peptides that only showed up in each fraction. Well, actually, it's fractionated by organisms, so we're looking at yeast, human, and E. coli data, and since they had collected, this was the yeast line, this was probably the human line, which was better. But now we just did one pool, or Ben just did one pooled thing that he ran twice, and so we're going to see much better IRTs. So that's a way of looking at library quality that Skyline makes very easy, and now we're going to go ahead and do that ourselves on the VMs. So I guess start up your VM. I don't have mine started. Okay, so who needs more time to get their VM started? Okay. So while people are getting their VM started, I'm going to point out what we're going to be looking at. I think for the sake of simplicity and consistency, what we saw yesterday was that people doing both TOF and QE was a little confusing. So this morning, since most people said they were interested in QE, we're going to be looking at the QE DIA course completed QE data. So this is completed. So it doesn't matter whether or not you actually managed to complete the tutorial. We're going to go play around with what you should have produced. And so in this tutorial library, we've got this iProfit PepXML, which are the results of the search. And since you saw how many search pipelines Skyline can deal with, you should be, and nobody raised their hand saying that they didn't see their search pipeline. So that means you all can start from here. And we're going to start from here today at this iProfit result. So that's just the result of a peptide search in DDA. And and then, we later in the week, we'll actually look at this transition list and the spectral library. So pretty much it's nicely alphabetical here. The stuff up top is the peptide search, and then all the spec lib in the middle is the spectral library itself, and then finally we get down to the peptide query parameters that are going to go into open SWATH. Okay, so the one thing that we need to do before we get started is we have the peptide search results, but we don't. Who remembers where the DDA data was? Like, it's not right here, right? And so Skyline, when we build a library, it's going to need to find this DDA data to get the spectra out of it. So we have to go back up to C DIA course data, and then DDA data, and then QE. So get to this DIA course data, DDA data, QE, and then there's some MZXML files. And now you have a choice. You can either, it's quickest to just move them. So if you, we're going to use them read-only, but you may want to move them back later. I don't know. So I'm just going to do Control X, and you can see they kind of gray out. So that's cutting them, and I'm going to paste them into that folder that we're going to work in today. So Control X to cut. And you could do Control C to copy, but that would add more, that would consume some disk space, and it would take time. So if we go to DIA course completed again, and then into library, and then Control V to paste, then now you should see that I get these, so I get MZXML right next to these individual PepXML files, right? So I've got an individual PepXML, and then eventually I've got this rolled up PepXML and iProfit here. So is everybody there? Anybody need more time? Okay, don't get lost now, because okay, so feel free to say you need more time. Okay, so then we're pretty much ready. Let's start up Skyline. I just have Skyline right on my desktop here, and I can double click on it or press enter, and I start here. So once you have Skyline running, what we're going to do is we're going to just use this wizard right on the first page, import DDA peptide search. So you just can click on that to start that wizard. And it says you must save the document, so we'll say okay. And whoops. And then if you get into this, if you're not already there, if you get into this, again, QE library folder where you should see no Skyline files, we're going to call this QE underscore DDA underscore library. And you don't need to type .sky because Skyline will put that on for you anyway. So just DDA, so you want to get to tutorial 1 library and then name your file QE DDA library. And click save. And that starts up this wizard. So the first thing we get asked is, what's our cutoff score? Who remembers the cutoff score from yesterday? That was the TOF one. Good job, though. You must have done the TOF data yesterday. So I can get it from here. There are actually these saved scripts, and the saved scripts contain this. So this is the cutoff value that was given from Mayu. And what do we get out of that? What's this cutoff value? It gives us only peptides with a protein false discovery rate of 1%, right? So go ahead and you can. I'm going to copy paste, but you can do 0.928079. So you don't have to find that file that I found. You can just follow along with 0.928079. So all that peptide searching and Mayu and all the stuff that you did, yeah. I think that's the QE one.
The triple top is the 977.
Yeah, so this is, see how I'm looking at QE run library generation RStudio win.sh. If I go to triple TOF, then, and I scroll down here, that's 0.9, so that's what he was saying, 0.977732. So trust me on this one. So this is the QE data, and that's what we're going to look at. And now we're going to go add the files just to remove any possibility of confusion. Since we saved the file in here, I think we should all come up in here, and we're going to choose. We got a bunch of choices because Skyline can build libraries out a lot of things, but we want this iProfit PepXML. So everybody click open. So now you should have your cutoff score, the file you're going to build the library out of. How many files are there in this library? How many DDA runs went into this library? 2. Okay. So we got 1 file, but it's a combination of 2. And then we want to also tell it that we're using the diagnosis, and we're going to use diagnosis 11. As Ben says, that first peptide in diagnosis can be a little unstable, and so sometimes we just use diagnosis 10. But and we're not going to keep ambiguous matches. Who knows what an ambiguous match is? So we did a peptide search. What's an ambiguous match? Yeah, so one spectrum that matched to multiple peptides, and we just don't don't have high confidence that that's going to lead to a good library spectrum for it's going to lead to a good library spectrum for our DIA. Okay, so click next. And so now Skyline goes into library building mode, and so it's a great time for questions. There's going to be a little bit of a delay.
Okay, if it reports an error,
What sort of error did it report?
could not find spectrum file.
So that means that you did not get your MZXML files in the right place. When we did that step to copy them from DDA data, you missed that step, or you put them in the wrong place. So yeah, so if it tells you, hey, I can't find the spectra, that means that the MZXML files are still somewhere elsewhere. How many people got that error? Okay, so the way you solve that, right, is you got to go back to tutorial library. So this is my DIA course completed QE, and you can see that I should have these Collins B PEP XML files as well as Collins B MZXML files. And if you don't have that in your DIA course completed QE tutorial library folder, then you have to now go find those MZXML files and get them in there. There are some search engines that don't require this. So Mascot puts the spectra right in the .dat files, but a fair number of them .group files from Protein Pilot. So there are a number, and XTandem, but some you actually have to have these spectrum files in order for Skyline to get them. Is everybody through that? Anybody need more time? All right. Okay, so well, let me talk about what I'm seeing now that my library build has completed. Is everybody here where they see this add IRT peptides? So we told it we had an IRT standard, and then Skyline is going to try to produce IRTs. And it says that it's producing IRTs for one file. Why isn't it producing IRTs for two files? We had two files, right? Well, this is a result of that plot where they were going all like this. I decided that doing IRTs based on the 10 or 11 IRT peptides wasn't stable enough to build a library. So we now do internal alignment of all the runs to as many peptides as they share. So that's one of the improvements that we did that I think gives us better IRTs out of DDA spectra. So there's this, it's not as interesting when it was successful, but you can click on this success link and have a look at the plot. And can we, no, okay. So this is the regression, right? So Skyline, in order to produce IRTs out of this data, has to look at the IRT peptides and do a regression to map measured times into IRT space. So this is what you should be seeing. Are people seeing this? Okay, so let's see, if we zoom in, why are the points not on the line? Yeah, so we're fitting a line, but what are the values that we're fitting the line to? What is this IRT number? Where did that come from? What? Well, they're just they're a unitless number, and actually, so the numbers that we're using here are just the original numbers that Diagnostics came up with on their chromatography. So it's just Diagnostics measured their own thing, and these are the numbers that are published in the paper. If you go up to the Biognosis site and look at the spec, these are the IRT numbers that they say are for their IRT peptides. And the fact that they're not on the line just means that they don't match my chromatography exactly, right? So now that's going to be important because Skyline's going to ask me a question as soon as I click OK. Is everybody here? Okay. So click OK, and then Skyline says, do you want to recalibrate the IRT standard values relative to the peptides being added? This can improve retention time alignment under stable chromatographic conditions. So that's just saying, like, you know, we can basically keep, you know, two of your points the same, you know, two of the points the same as the Biognosis standards, and then everything else we can just actually calibrate to your system. And that ends up, you know, giving you a little bit of extra. If you're really just building this library for your system the way we are, you know, the way this is, and we have a very promising setup in that Ben measured the DDA runs that we're using on the same chromatography that he measured the DIA runs. And if that's the case of what you did, I would suggest that you click yes here. And if you're just trying to build a general library for other people to use, I would suggest that you click no, because then it'll just be confusing to other people when you pass around this library. Why aren't you using exactly the specified IRT values? But we're going to click yes. And that's just going to make, you know, shift all the IRT values so that they're exactly on that line. And we'll see that in a second. Okay, so now Skyline's saying, okay, I want to do chromatogram extraction from your MS1s because you told me you're importing DDA data, and it's found the MZXML files that it can do that from. And thankfully, Ben included the MS1s in his MZXML. If he hadn't, we might have to click this button and go find some raw data files. But he didn't. So there's MS1s in these MZXMLs. It's possible to export MZXMLs or MGFs or some file format that contains only the MS spectra. And in that case, Skyline still might suggest, hey, I'm going to extract chromatograms out of here, but you might not be able to, and then you have to go find the raw file. So that's why there's this exclude spectrum sources, and then it allows you to go click find the original data that has the MS1. So we're going to also say files to import simultaneously several. Yeah.
May I ask something on the IRT calibration curve? Why don't we have two of them? I mean, I would expect we have two samples, right? Two DDA runs, that for every one we would have a calibration curve.
Yeah, so that was that's what we had originally, and what I ended up feeling was better because of that plot where I showed the rocket fins coming out, that there's too much variability in aligning just 10 points, and so when I have DDA data, those two spectrum searches share thousands of retention of peptides, right? And so what I do is, or what Skyline does now, the code in Skyline, is we align the runs to each other based on all the points that they share, which are going to be thousands.
Is like an average of them?
No, we do that same kind of regression to do alignment. So we're doing exactly the kind of thing that MaxQuant does. That, you know, it's retention time alignment of DDA data using all the points that we know that they share. So rather than doing a single regression, so then we map everything into a single retention time space, and then we use the IRTs in that space to create one regression for everything. And that leads to just a more consistent set of IRTs. So, and that helped me. I showed you that case where, well, with the rocket fins and you know, the rocket looking like it's taking off, I made some changes to how Skyline calculates IRTs from spectral libraries, and that helped get the rocket ship to look more like that second line that I had produced So what was there's another question? Yes.
Didn't you have the same chromatographic method that to do this alignment? Because if you have different chromatographic method, like different for size,
Mm-hmm. Yeah, it's definitely expected. It's expected that you're not mixing chromatographic methods. Yes, you should not think that you can mix chromatographic methods into an IRT library. There's no way of specifying, this is for this pore size or this is for this pore size. The only way that you specify is by having a different IRT library. So yeah, you're expected to keep your chromatographic methods similar, although if you go read the IRT paper, we did change the gradient length. So we went from a 30-minute gradient to a 90-minute gradient, and you can read about how that went. It worked fine.
You can merge the IRT libraries afterwards if you build them separately, I guess.
You definitely can, but you shouldn't do it for different chromatographic methods, right? So if you you want to do it for IRTs that are going to predict on some chromatography, and you want to tell people, okay, this is for C18 chromatography, blah, blah, blah. You're going to give them a file that is your IRT library, and there's no space in that library to have like 5 different methods. You can have one method per library. But yeah, there's all kinds of, as long as they have the same type of chromatography, you can merge IRT libraries in Skyline. Okay, let's keep going. So yeah, we're going to import several. We have some more settings to set up. So those are our files. Click Next. And now Skyline's saying, hey, I see that you have a common prefix. Frequently, having a long common prefix will just make the UI in Skyline less usable. So Skyline offers to remove things. I'm going to backspace over the 1 and 7 so that I get the replicate names 177 and 178 rather than just 7 and 8. So this is what my replicate names are going to be. I don't really need the columns be X1803. So click OK. Okay, so we're going to allow precursors 2, 3, and 4 charge states. We're going to extract 3 isotopes. So for each one of these, we're going to have just the monoisotopic, the M+1 and the M+2 extracted from MS1. So this is MS1 filtering. And the data is centroided. I'm going to go ahead and use 20 ppm because that's what I saw Ben was using in the tutorials. We're going to hopefully get to an analysis where we show that Skyline's default of 10 ppm works just fine on this data, but that will be later in the week. And then we'll go ahead and extract 5 minutes of MS-MS. We could certainly do narrower, but it's nice to have you get a little bit of the sense of what the chromatography is like if you go wider. And mostly this is going to be a choice of how much disk space the chromatograms are going to take up when it's done processing. So I'm fine with 5 minutes. So it's 5 minutes within the MS-MS ID. So in general, we're going to get 10 minutes of chromatogram. So that's 5 minutes on either side. Click Next. Okay, so now we have to, we're going to allow 2 miscleavages. And then we're going to browse for the FASTA file. Who knows where the FASTA file is? The FASTA file is, so we go back up to the root of C under DIA course data. This is the NProto 3 mixed human yeast E. coli FASTA file. So that's what we want. Everybody got that? So that's the main DIA course data folder. Would be nice to have a shortcut for that one. And then we just open this IRT reverse FASTA file. So this says that it's got mixed human yeast E. coli plus the IRT peptides plus reverse sequences for decoys. So click open. And everybody here? No? Okay, well, go ahead and click finish because it'll get started and take a while, but I'll sit on this page for another second for people to catch up. Are people on this page trying to find the FASTA file? If you're behind, how far behind are you? Okay, well, I'm going to click OK too, so then it will start doing the extraction. So I'm going to click finish. And the first thing it's going to do is it's going to analyze that. Oh yeah, it's going to offer me some. So it's going to analyze the FASTA file first, and then I think it's going to offer me some options before it actually starts extracting chromatograms. So, and you can see that it's going through proteins, and some of them are reverse underscore. Those are the decoys that were used in the search. And when I get to the end, Skyline's going to show me, so it shows me that, okay, we got 16,600 peptides, 18,300 precursors, and having 3 transitions each is going to give us 55,000 transitions. And we got 3,890 proteins. So here now we get to choose. We could say, oh, I only want to take proteins that have 2 peptides, which drops me, I lose over 1,000 peptides. So let's not do that. Although that's a very reasonable choice. We're not going to do it today. But we do want to get rid of the duplicate peptides. And that's going to lose us about 600 peptides. So 600 peptides are duplicated in multiple, that's 600 proteins. 600 proteins have only one peptide, and that peptide is duplicated, or they have multiple peptides. But all of their peptides are duplicated, and we lost 3,500 peptides. So 3,500 of the peptides are not specific to the proteins of interest. So we're going to go ahead and do that, and keep that in mind, because the library and query parameters that you created keep those duplicate peptides. They just sort of stick them off into strangely named proteins, so that they have proteins with only unique peptides, and then they have other sort of multiple proteins so they keep everything in those query parameters, and we'll see that later. But for the moment, we're just going to do the simple thing, which is just remove duplicate peptides. You could also do remove repeated peptides, and that would actually keep all the peptides. So you can see that there's actually only 14,400 peptides. Repeated peptides would keep all the peptides, but it would remove the second occurrence of them. And you can see even that gets rid of some proteins. So even keeping all peptides, we really only have 14,400, and this 16,600 is with duplicate peptides. So it's not; those aren't really unique peptides. So we're going to just remove the duplicates for now and click OK. Has everybody caught up? Okay, good. Long enough explanation. All right, so then we click OK, and now Skyline puts all of those proteins and peptides into my targets list. And you can see it puts the IRTs up at the top. And I've got 2 replicates where it's going to be extracted. It's going to be putting extracted chromatograms. And I've got this thing showing me the progress in Skyline of the chromatogram extraction. You can see it's going pretty quickly. I can hide this by clicking hide, and then I can bring it back up at any time by pressing on this chromatogram button down here. So let's have everybody press this little push pin. So press the push pin. That will keep the window up after it finishes, so that we can see the final results. So it's made it through the chromatogram extraction, and it did it so quickly that Skyline's a little behind on peak picking. So Skyline is still trying to figure out what are the chromatogram peaks to integrate based on the IDs and other scores. So let's also maximize the Skyline window so it takes up all the space. So just click the maximize button or double click in the title bar. And we can start arranging other windows. This is this library match tab. That's going to show us the, well, actually it already will show us if you expand the IRTs. So expand, and you can see the IRTs have a set of icons with little clock faces, which is how you know your IRTs are set up acceptably. And then you can click on one of the top IRT, and now you'll see a spectrum. And you'll notice that this spectrum has quite a lot of Y ions, and it's got some noise, but if you right-click here, maybe some of those are B ions, because by default, we're just highlighting the Y ions. So right-click and choose B ions in the library match, not many there. You can also choose to add charge state 2, and maybe we get a little bit more. And then you can kind of just go right down and look at the spectra for the IRT peptides. You can see that above here there's there's a QE, there's a spectrum drop-down list which shows us where. So this library contains redundant spectra, or spectra that are not, they're not redundant in the way we were talking about before, but this library contains spectra, and these are all the times at which we saw them. All right, so I'm done with extraction. Who else is done with extraction? Okay, that's the great thing about having VMs. If we all click go at the same moment. So it should take about 3 minutes to get through both of those. And then you can close that window. And now you'll start to see the chromatograms for one of these. If we go to view arrange graphs tiled, you'll see the chromatograms for both. And you can see the IDs. I'm going to go to view auto zoom best peak, and remember that that's F11. And now you can see that there are IDs, multiple IDs per peptide, and you can click on these IDs and look at the spectra and how similar they are. Well, so the ones that are on the edge of the peak are quite similar, right? And then when I get way out to the end here, there's something, this is probably a chimeric spectrum, right? And with any of these graphs, if you want to zoom the y-axis, you can just click on the graph and put your mouse to the left of the y-axis, and then I can use the mouse scroll wheel or two-fingered zooming to zoom way in and kind of go, yeah, okay, I guess, yeah, this is definitely not the only thing that's in this spectrum, but maybe it's there. And you can do that with the other one too. You can, and then anytime when you're zoomed in too much into a graph like this, you can right-click and undo all zoom and pan. And so that one looks pretty good. And yeah, you can see that even across runs, we get fairly similar spectra here. And that's the principle that will allow us to extract them from DIA. All right, so let's bring up a few more of Skyline's default views. If we go to view retention times, replicate comparison, and you could remember that that's F8. That will bring that one up. And then we can go view retention time peak areas, which is F7, replicate comparison, F7. And now you can see that we get an I.P also, which is a similarity score between the expected isotope distribution, which is here on the left, and what we're actually seeing, and they're quite close to 1, which they should be. So let's take this, and we'll take the, now we're gonna start docking windows. So hopefully by the end of this course, if you're gonna use Skyline going forward, you should master this pretty well. Click on the title of peak areas, and as soon as you start dragging, you get this blue rectangle, and you can start to see docking indicators, where if you put your mouse cursor inside the box, the rectangle, for a docking indicator, then Skyline will show you where it's going to dock the window. And we want to just dock this peak areas window right on top of the spectrum window. So if you if you bring your mouse into the library match window and then into the center of that cross that shows up and release, then now you have a tabbed window, and you can click the tabs at the bottom to switch back and forth. So that's where we're going to put our peak areas window, and we're going to take our retention times window and drag it on top of the peak areas, but instead of doing it right on top, we're going to do it below. So just drag your cursor until it's on the bottom rectangle, and there's a blue rectangle across half of the peak areas window, the lower half, and release. So there you go. Okay, so now, what are some things we might want to look at well, okay, so first thing, when trying to decide what's the health of your spectral library, it's okay, it's a good idea just to go view spectral libraries. So click View Spectral Libraries, and Skyline has a spectral library viewer. You could even add that Spectrast library and have a look at your Spectrast library too. Skyline supports Spectrast and other library formats. So, but this is the one that we just built. It's our only library. You can see that there are 15,890 total precursors. And so we have that means that, like this one here, you can see has the charge 2 and charge 3 of the same peptide. And you could run through and view the spectra. And there's 2 other things besides the spectra looking pretty good that you should be looking at here. And those are, well, that you have these icons here. That's 3 things, I guess. You have icons here, which means that Skyline understands what these peptides are, and you could add them to your document, although they're already added. And then you have a file indicator telling you what file they came out of, and a retention time indicator telling you what their retention time was. And that's what controls those ID spikes that show up. So everything's looking good. The one last thing I would do is click on this ... button next to the name. And here you can see a summary of that, there were 26,486 matched spectra with 1,590 unique precursors. So, not a lot of, we only had 2 runs, so not a lot of duplication. And then you can see sort of the health of each file. We've recorded the cutoff score that we used. The score type is peptide profit something. And then, yeah, you can see that each run matches about the same number of spectra, and there's slightly more best spectra in this second run. So close that, close the library viewer. Okay, I'm running out of time here, so the last 2 things we're going to look at are just, we would like to know, well, let's get to that retention time one so that we know that we didn't just forget that. So go to View, Retention Times, Regression. So this is what I said we were going to look at. So now we've got peaks that were picked, as well as we've got IRTs. So I'm going to pull this out. It just docks with the other retention time view. I'll pull it out and make it big. So the line is the prediction from our QEDDA library. So that's an IRT library. Those are our IRTs. And then these are the measured times. And so there are some things where we end up finding peaks that are not exactly the same, and I don't know what's going on with that. But most are pretty close to the line. And we can right-click and then plot residuals. And that will give us something, that looks like what we've just been looking at. And then we can zoom in by putting the cursor left of the y-axis, and we can see that we're finding peaks. In this case, there might be a teeny bit of a slope, but we're finding peaks within 1 minute. And I guess I guess I'll let these guys get set up. But so that gives us some idea of how our IRT health is. We're going to look at it again when we actually extract DIA data. Another quick thing you can do, there's a lot you can do in here, and I encourage you now have a document, play around with it, and look at your library health and look at the health of the data that you use to build your library. So another thing you can do is look at the mass errors. So if you go to mass errors histogram, that's unfortunate. It says unavailable mass errors. So what you have to do is actually go to transitions and choose precursors, and then this will tell you that your mean mass error is 2.3 ppm off center, and a standard deviation of 4 ppm. So that, if you just look at this, you're like, yeah, probably plus or minus 10 ppm would work pretty well. But we're using plus or minus 20 ppm, which is plenty of space to be extracting these precursors. So those are other sort of health diagnostics you can look at, and I encourage you to play around with this file and see what else you can learn about the library data. And then tomorrow, once you have some experience with Skyline and some experience with DIA processing, we're going to come back and go through this, build the library and extract DIA data from it.